4 chapters. The first chapter was actually the general drive system. The second one also it's related to the torque speed characteristic. The third and the fourth is related to the DC machine. So chapter 2 was the modeling of the DC machine. Chapter 3 was the control rectifier based drive system, the steady state analysis, and let's say the dynamic modeling. And the fourth chapter was the DC to DC or chopper based drive system, correct? So now we will discuss what? The polyphase induction machine. So now we are going from the DC machine to the induction machine. Now, in general, as induction machine, any machine consists of stator and rotor, whatever the type of the machine. Even if it's linear machine, it should consist of what? Stator and rotor, or there we call it stator and mover, the moving part and the stationary part. Here is no exception, which means that I will have a stator. This is a picture of the stator. You can see what? Slots. In those slots, we will have winding. Those windings should be distributed in space such that the angle in between is what? 120 degree. Why 120 degree? Because it's a 3-phase system. If I'm having 5 phases, I will have what? 360 over 5, 72. Yeah? So 120 degree because of what? Because of the 3-phase system. I need to distribute the winding in the space such that I will have 3-phase identical distributed in space by 120 degree. Good? Good. Now this is the stator. In the rotor, I'm having 2 choices for the rotor. The first one is what? Is the squirrel cage, the most famous one, the squirrel cage, which means that the rotor has no winding. It's bars shorted by a ring. So this is the, let's say, the picture of the squirrel cage, and this is the actual, let's say, picture of the actual squirrel cage rotor. Here I don't have any windings. Right? And simply, why we call squirrel cage? Because of the shape. Yeah? And simply you can see the bars. Do you see the bars? Yeah. The bars is not, let's say, straight. They are skewed. Or let's say there's a deflection. Yeah? Do you know why here? Why those bars are not, let's say, straight?
عشان تغطي الفترة اللي بيكون فيها الفيز، عشان تكون أكبر فترة aligned مع الفيز.
No, no. You know the distance. The distance depends on what? On the angle. Yeah. So this is what I'm maximizing the distance. Yeah, the length. If I'm maximizing the length, I'm changing what? The resistance. Correct? So this is a way how to change the rotor resistance actually. Correct? Correct? This is the first choice. The second one, we call it the wound rotor, which means that the rotor actually contains windings, so there's slots in the rotor, and in that slots, I'm having what? Winding. And those windings are connected to external circuit. So if I need to connect them to external circuit, in this case, I need a slip ring. Why? Because the rotor is moving. How come I can connect a moving part to a stationary part? So I need what? Slip ring. I need a slip ring, which is a brushes and a ring in order to have a connection between the rotor and the external, let's say, supply or external resistance. Yeah? Good. Now,
السكار الكيج ما له سليب رينجز؟
no, there's no slip ring.
كيف بكون معلق جوا؟
إيه؟
كيف بكون جوا الموتور؟ بكون
no.
لابس يعني؟
Now you are asking about how the parts are fixed to each other. Yeah?
بس
So simply there's a bearing. Bearing. Yeah?
تمام.
In order to fix the rotor in the center, it must be elegant in the center. So there's a bearing. Yeah? You see the bearing here? Now the next slide actually will give you a picture about that. The first thing, this is the, let's say, the outer picture. If I'm having a cross section for that, this will be what? The induction machine contains all of the elements inside the machine. Now, this is the assembly of the machine. Assembly, it's from the fan cover until the bearings. Yep. This is what? Squirrel cage or wound rotor. It's written here. This one is squirrel cage. Yeah? It's written here. Squirrel cage induction machine, or simply there's no slip ring. So this is a squirrel cage induction machine. Now, if I'm referring to the squirrel cage induction machine, this is a rigid machine, which means that it can plug and play whatever the environment. Yeah? It's less expensive compared to what? To the DC machine. Now, if I need to compare, I need to have a reference. Until now, what we have, the DC machine as a reference, correct? Now, if I'm comparing the squirrel cage induction machine with the DC machine, why I'm excluding the wound rotor? Because there I'm having slip ring. In the DC machine, I have slip ring. So this will need a maintenance, and that will need a maintenance. So I will take advantage for the polyphase induction machine, the three-phase induction machine, which is the horsepower actually is what? Is the squirrel cage induction machine. Here I don't have any slip ring, so I don't need to do a maintenance. There's no brushes. Yeah? This is a rigid machine, compact machine, which means that if I'm comparing two machines, yeah, same rating, I will see that the induction machine has less volume, which means that it will have more torque per volume. Yeah? Good? Good. Now, you know that the induction machine is a plug and play machine, which means that if you plug it in the three-phase supply, it will rotate. Yeah? How's that? Let's assume here I'm having a three-phase winding, A, B, and C, and the same thing here. Even if I'm having, by the way, a squirrel cage, the equivalent circuit, it will be what? A winding. But those windings are what? Are shorted by each other, correct? Yeah? Now, you know that at first, if I'm energized, the stator by a current, this will produce what? Flux. Yeah? Now, this flux will induce what?
Voltage.
A voltage where?
Rotor.
On the rotor, correct? Now, because the rotor is closed, either shorted, a squirrel cage, or I'm shorting the terminal, if it's one rotor. In this case, the induced voltage will cause what? A current to flow. Now, that current will produce what? A flux. It will rotate with what? With the main flux. By the way, it has the same speed. The flux in general, it has the same speed. But the rotor will rotate in a speed less than the synchronous speed. So here I'm having, let's say, the synchronous speed, which is called NS. Yeah, it's 120, the frequency over the number of the balls. Yep. And simply, I'm having what? The rotor speed. In this case, the difference in between is called what? The slip speed. Yep. The difference in between is called what? The slip speed. Now let's see the idea of the rotating field. So simply, if I'm energizing the phase A with a certain voltage, in this case a flux will be generated, and this flux can be represented as, let's say, phi A will equal phi max sine omega t. Phi B will equal phi max sine omega t minus 2 pi over 3, and phi C will equal phi max sine omega t plus 2 pi over 3. Yeah. Now, time, the flux will be, the flux of the phase A will direct toward AX. It's governed by what? Actually, by the right-hand rule. Correct? And the flux of the B will direct toward the axis of the B. The same thing as C. Now, because the current is alternating, the amplitude will change. The amplitude will change, but the direction will be what? The same. All the time, this is the axis. Yeah? All the time I'm pointing toward A, B, and C. 120 degree between them. Correct? So let's take 3 points, T1, T2, and T3, and calculate. At T1 is actually equal to what? Pi over 3, correct? You see it?
Yes.
Yeah? So, at this point, the flux due to the phase C is equal to 0, correct? Yeah? Now, the flux due to the A, phi A equal to what? The maximum flux sine the angle, which is the pi over 3. And this will equal to what? Square root of 3 over 2, the phi max, correct? Yeah? Now, the flux due to the B, so here I'm having a vector. The length of this vector is equal to what? Square root of 3 over 2 phi max. Yeah? The flux due to the B will equal to what? Phi max. The angle will be what? Sine pi over 3 minus 2 pi over 3, and this will be minus the flux max sine pi over 3, correct? You know that sine of minus theta equal to what? Minus sine theta. So this equal to what? Minus square root of 3 over 2 phi max. So simply if I need to put it, where I will put it? The opposite to the flux P, correct? It's minus. So it will be here. Yeah? Now, can you find the resultant? Yes, simply. We know that this vector is equal to what? Square root of 3 multiplied by the length of the vector. So it will be 3 over 2 phi max. Correct?
Yeah.
So this will be the first one, correct? So this is the resultant. If I'm taking at t equal to 2, it will be here. So now what will happen? Do you see the total flux is rotating, correct? Yeah? It's rotating. And this is the idea behind what? Behind the rotating magnetic field. Yeah? Now, the flux is rotating by which speed? By synchronous speed, correct? By the synchronous speed. So if I need to calculate omega s, this is equal to what? 2 pi fs. Now this is what we call the electrical speed. Yeah? Which what? Simply how much time the flux need to complete one cycle, correct? One cycle. Now the period, you know that the period is 1 over the frequency. Yeah? And if we need to calculate the speed of the air gap flux, which is omega s equal to pi fs, and we know that we have a relation between this is as radian per second. If I need to have it as revolution per minute, this is equal to what? 2 pi over 60 multiplied by omega s, and this will be what? Rad per second. Yeah? Yep. Now, here I said electrical speed.
RPM.
Ah, thank you.
كأنه كنترول بي
RPM.
شايف ذيك المرة اللي ريزر كانها كنترول اي بس ناسي كيف ترجع البن إلى اختصار ثاني المحل
check it, huh?
Oh,
But you forget. So next time.
that's it.
Now simply, if I'm assuming that I'm having a two-pole machine, so this means that here is the north, then here will be the south, and so on, correct? In this case, this is the north, and this is the south. Now, this one period, which is the two-pole. If I'm having a two-pole, in this case, the electrical angle and the mechanical angle will be the same. Yeah? Now, if I'm having four, let's assume this is a north, this is a south, this is a north, and this is the south. Now, what will happen here? Here I will have a north, south, in one revolution, correct? Yeah. One mechanical complete cycle, I will have two electrical cycles, correct? Yes? North, south, north, south. Now, from the electrical point of view, this is what? A complete cycle. This is the two-pi. From mechanical point of view, this is the complete cycle, correct? So now there's a relation between the electrical speed and the mechanical speed. Yeah? So let's say omega S electrical will equal to what? Will equal P over 2 omega S mechanical. Now, if the number of poles is 2, in this case, the electrical speed is equal to what? To the electrical speed is equal to the mechanical speed. Yeah. Now, if the number of the poles is 4, in this case, what? The electrical speed is twice faster than the mechanical speed. Yeah. And this is the number of poles. So here simply the same thing. If I need to calculate NS, it will equal 120 multiply the frequency over the number of the poles, and this will be revolution per minute. The same thing here. If I need to calculate the slip, it's actually delta n over ns, or delta omega over omega s, and it's ns minus n over ns. And this is the relation between the speed in radian per second and the speed in RPM. Now the equivalence circuit. Now you know that the rotor and the stator, there's no coupling, there's no electrical coupling in between, yes? The only coupling in between is what? Magnetic coupling. So simply here, I'm having here a circuit, a rotor, and what? Distance. Now, due to the slip, the frequency here is what? F here is equal to what? F of the supply. F of the rotor here equal to what? S. Fs, correct? Yeah. So in this case, this will be what? If I need to use the frequency, you know that if I'm giving you any inductance, it will be given according to what? To frequency. So in general, we will give what? The frequency of the stator. Yeah? So here, because the frequency is what? Is SFS, here I will have what? S here. And the same thing here for the induced voltage. Now I need to do what? I need to have electrical coupling. I need to refer, let's say, the rotor to what? To the stator. So the first thing I will do is what? To divide here by S. Yeah? If we divide here by S, what will happen? So if we divide here by S, I will get here E2, here X2, and here R2 over S. Yeah? Now you know that in general I need to find a relation for the torque. And if I need to represent a power in electrical circuit, I need what? I need to represent it by a resistance, correct? So in this case here, I will divide this one to two parts. So R2, and I will end up with what? R2 over S, 1 minus S, the same thing, yeah? Then I will try to refer the R2, if I refer it to the stator, it will be R2 dash. And N1, N2 is what? A turn ratio, yeah? The same thing for what? For the X, yeah? So simply this means that here, I will have, this is, let's assume, RS, this is JXS, let's assume this is the JXM, here JXR dash, let's say, and here I can end up with the resistance, which is the R dash over S, correct? Yeah? Now, if I need to find a relation for the torque, I can do approximation. The first thing, the drop voltage here is negligible, which means that Vs here and here is E is almost equal to that. Yeah? So we can say that E is almost equal to what? To Vs. If this is the case, then simply I can reorganize the circuit such that the magnetizing branch appear here, correct? Yes. Now this is the magnetizing branch. Yeah? Now here I will have what? X equivalent, which is actually what?
R1 plus R2.
X1 plus X2 dash. Yeah? And here I will have what? R equivalent, which actually what? R1 plus R2 dash. Yes? Yeah? Yes. Good. Now, this is what we call the pair phase equivalent circuit. This is what we call what? The pair phase equivalent circuit. Now, from the pair phase equivalent circuit, actually, why we need the pair phase equivalent circuit?
Because we are taking, analyzing just one phase.
Yeah, I know. But why we need that?
ثلاث زي بعض بس بينهم angle shift.
Yeah, I know that I need only one phase in order to study the whole the machine. In the end of the day, I will multiply by 3. But the question, why I need the pair phase equivalent circuit? Yeah, in order to find what? Mathematical. Yeah, mathematical relation. Yeah, between the electrical quantities, let's say, or electrical variable and the mechanical variable, the developed torque, correct? Now we can track the power, correct? We can track what? The power. Now, if we track the power, the first thing here what we have? The power input, correct? We have Bn. And Bn in general it's equal to what? 3-phase system, so 3 V phase I phase cosine theta, or square root of 3 V line to line cosine theta, correct? Now part of the power will be dissipated where? Across the stator circuit, correct? Yeah. So this is the Bn. So part of the power will be P copper losses of the stator. And this is equal to what? Yeah, it's 3 because I'm having 3 phase. I1 or S, let's say S stator square, RS, correct? Sometime the core losses is already augmented here. So we say that this one augmented here with the copper losses. Yeah? So in this case, what we'll have? The power in the air gap. Now the power in the air gap will equal to what? Now let's see. Do you remember this circuit? Now we are here, huh? Until now. This is RS, XLS, let's say, XLR dash, RR dash over S. Now, this is the power on the air gap. Now, the power in the air gap will equal to what? The power dissipated by this resistance, the total resistance, correct? So the power in the air gap equal to what? 3 I R dash square R dash over S. Yeah? Now part of this power will be dissipated as a copper losses where? On the rotor. So here I will have P copper losses of the rotor, and this will equal to what? 3 I R dash R dash, and the current is square, correct? Now after that what I will have? The converted power, let's say, the power converted or the power developed. Yeah? The developed power. Now the power developed will equal to what? Simply it will equal the power on the air gap minus the power on the copper losses due to the rotor. So this will equal to what here? 3 I R dash square 1 minus S over S R dash. Do you remember that this one can be separated in two resistance? One is fixed, which is the R dash, and the second one is variable, which is the 1 minus S over S R dash, correct? Yeah. So this one represent what? Will represent the copper losses on the rotor, and this one will represent what? The power developed. Now here, from the power developed, actually I can calculate the developed torque. Yes? Okay. Now we know that the power developed will equal TE multiplied by omega mechanical, correct? Yes? So if I'm having the power developed, if I divide it over omega mechanical, what I will get? T, correct? Yes? Yep. Okay. So if I need to calculate the power developed, what I need to calculate? I2 or what we call it IR dash, correct? Now how to calculate the current? Simply if I'm assuming that I'm having the simplification such that the delta Vs is equal to 0, which means that this branch can be moved here. Now IR is very straightforward, correct? IR dash will equal Vs over the impedance Zn as seen from here, correct? Now this impedance is very straightforward. It's actually two impedances in series, correct? Yeah? So it will be what? R1 plus R dash over S plus the X equivalent. Yep? So now this one, if I substitute it here, I will get the developed power. If I divide it over omega m, I will get what? The developed torque. Yeah? So this is the relation that specify the relation between the developed torque and the machine variable, let's say. The voltage, the rotor resistance, and the frequency, let's say, correct? Those are the variables. If I need to change. Of course, if I'm not discussing the design stage, which means that I will not change the structure of the machine, the only thing that I can change is what? The voltage, the frequency. Yeah? Now, if I'm having one rotor, then I can change R2 by connecting an external resistance to the rotor. If I'm having squirrel cage, R2 option is not valid because there's no way to change what? The rotor. Yep. So I will end up with what? With a voltage and a frequency. Yes? Now someone say also you can have what? Change the number of the balls. Correct? Omega was equal to what? Omega S or an S, let's say. 120 F over P. So if I'm changing P from 2 to 4, I will change the frequency. Yeah? From 3000 to 1500. But someone will say this is actually restricted to a special purpose machine, which means that I need a machine that I can reorganize the winding such that I can get different pole number, correct? And this is a special type machine. You cannot find it in the market. You cannot find it in industry. In the lab, yes, you can find, but no one uses it. Why? It's only has two discrete value for the speed, either 1,500 or 3,000. Yes?
Yeah.
So let's say that this one is not option to control the speed. So now we'll end up with three options: voltage, frequency, and rotor resistance. If we exclude the wind rotor, we'll have only two options. Yes? Which is what? The voltage and the frequency. So before discussing in detail how we can control the voltage, how we can control the frequency, let's try to plot the torque speed characteristic. Yeah? So now,
دكتور ويند روتر بنغير
external resistance.
external resistance صح.
It's option. For the wind rotor, I'm having three methods to change the torque speed characteristic or to control the speed. In the end of the day, if I need to control the speed, I need to modify the torque speed characteristic. Yeah? Because the intersection between the torque speed characteristic of the load and the machine will specify the operating point. Yeah? So if I'm not changing the load, in general you will not change it. You should live with the load. So the only thing that you can do to change the speed or to control the speed is to change the torque speed characteristic of the machine. To shift, let's say, the intersection point. Yeah? So this is the only way. So now, let's see. If this is the speed and this is the torque, here I need to specify 3 points. The first one is what? The no load speed. Here, this is the maximum torque, and this is what?
Starting.
The starting. Now, someone say the starting from the name, starting the speed equal to what? 0. So the slip will equal to what? 1. Do you remember the slip? This written here. The slip equal ns minus n over ns, and n is the rotor speed. So the rotor speed at standstill, at stopping, equal to 0. So the slip here equal to 1. Yeah? So at this point, this is the maximum torque. The maximum torques will specify T max and S max. If this is the, let's plot here a K, which is that. So now, at this point, the slip equal to what? 0. At this point, the slip equal to what?
1.
At this point, the slip equal to what?
Maximum.
S max. We call it S max, right?
Yeah.
Now, if I need to plot, I can do approximation. Yeah? I can say at low slip and high slip. Correct? Now, the operating point actually is the intersection point between the torque speed characteristic of the load and the machine. Let's assume that I'm having the following load, TL. Now, the operating point here, where? This point, huh? This point, correct? So simply this is actually will be what? Let's say an R, correct? Yeah? Correct? Good. Now what about this one? Where's the operating point? Let's assume this is T load 1, TL2. Here.
2 operating point, 1 stable, 1 unstable.
Who agree with الأولى ولا الثانية؟
الخطين لنفس اللود.
No, TL1, TL2. I'm changing the load. I need to specify another operating point. 2 operating modes, so you agree with your friend.
1 is stable, 1 is unstable.
1 is stable, 1 is unstable. Who agree? Abdullah, شلون ولا شلون? You agree? There's no way. The machine can start. The machine will never start. Yeah? Simply the starting torque is less than the load torque, so this is the block rotor. The machine will never start. You see? So simply here, the machine will never start. Yeah? Now, as you can see, here I'm having 2 regions. One is seen as to be linear region. Yeah? From the shape, it's almost linear. And one is what? Seen to be non-linear region, or what we call it the stable region and the unstable region. Correct? Yeah? And for the machine to operate at a stable point, yeah, it must be operating at what? At the linear region, yeah, with a starting torque higher than the load. Otherwise, it will never start. Yeah. So now let's try to find an approximate, let's say, solution for the small slip and the large slip region. For large slip mean what? S is equals to 1. Huh? S is equals to 1. In this case, if I need to compare, this one will be higher than this one.
Yes.
Yeah. Yes?
Yes.
If that's correct, then I can neglect this one, correct? I can say this one is also almost negligible. Yeah? So I will end up with what? With a torque which can be represented by what? This relation. Huh? So here, the torque is inversely proportional with the slip. Correct? So if I need to plot it, yeah, it will be what? Inversely proportional. Yeah? Now, what about for a slip which is what? Small, which means that I'm near the synchronous speed. Yeah? In this case, I'm dividing by very, very small value. So this one actually will dominate this one and this one. Correct? Which means that the torque now is proportional with what? With this slip. So those are what? Two approximate relations. When you can use it, if I'm not saying, if I'm telling you that you're allowed to use approximation, this is the first one, or if you need to do, let's say, some kind of ratio. I need you to calculate, for example, the starting torque at certain voltage as a ratio of its what? Rated value. So in this case, you can use this one with no hesitation. Even if you use the first one, the complete torque, it will be the same. Why? Because the factor will cancel each other and you will end up with what? With a ratio between the voltages, let's say. Yep. Now, how to find the maximum torque? So until now, we specified the relation between the slip and the torque at high slip and at low slip. Yeah? So now we have a plot for the linear and the non-linear. Now we need to find the intersection point to connect the two graphs, which is the maximum. So I need to find the maximum torque. How to find the maximum torque?
Take the
Derivative. Now if I need to find a maximum of a graph, I will say what? It will be at the maximum, the slope should be equal to what?
0.
So I will differentiate the torque with respect to S and equal to what? To 0. Then I will solve this relation with respect to S. I will have what? S max. Now this S max, if I substitute it in the torque, I will get what? T max. Yeah? So this is the torque. The first thing I will differentiate with respect to S in order to calculate what? The S max. After that, I will substitute it in the torque to get what? T max. Now, one comment. S max depends on R2, which is the rotor resistance. T max depends on R2. So, whatever you are doing, you will never change the maximum torque by changing what? The rotor resistance. But you can shift the location of what? Of the maximum torque. So sometimes I need to maximize, for example, or I need to design a machine such as the maximum torque at start. Which means, let's assume that I'm having the following torque speed characteristic. That's replotted like this one. This is a standard torque speed characteristic, correct? So here, this is the torque, and this is the speed and slip, correct? Now this is the T max, S max, correct? Imagine that I can put this one here.
Yes, I will.
So simply it will be something like this, yeah? Yeah? In this case now, for this curve, S max is equal to what?
1.
1,
One.
yeah? And T max is equal to what? T star. How to get T star? Simply, if I need to find T star, Maysaloon, how to find T star? At T star S equal to what? So substitute here by 1, you are getting what? So it will be T developed at S equal to what? To 1. Now this machine actually is called class D machine. And this machine is called class A machine. Now we have class C, we have class B, but simply let's say that I need only to discuss with you class A and class D. Now, let's see. What the difference between class D and class A?
maximum torque.
Hmm?
مكان maximum torque.
Now, someone will say class D has high starting torque compared to class A. The second thing, class D has a wide linear region. You see, I can control the speed from here to here. But simply class A has what? A narrow, yeah? Speed region to control. Yeah? In terms of the efficiency, which one has the higher efficiency?
Class A.
Why? Class D, class A. Why?
Class A. في resistance, في losses.
Yeah. Now someone said that I'm adding resistance, so I'm what? I'm generating heat. Someone said, wait, I'm discussing what? From the box machine. I'm having class D machine and I'm having class A machine. I'm not adding any resistance. By the design, I'm designing the machine such that class A or class D. Look to the class A, class B. Let's assume the same torque for the same torque. So for the same torque, let's assume that I'm having for the same speed, let's say. Oh, let's Control Z will not work, huh?
Control E.
Control E, thank you.
بتصير مساحة المفروض ولا إذا بتكسر
Yes.
بس ناسي اللي بتوجعك على القلم.
Okay. So let's go the math. So let's assume that we have the following torque speed characteristic. Yeah? Now, which one has higher slip? Class A or class D?
Higher slip.
Yeah.
D.
D. Now, do you know the relation between the slip and the efficiency? If you don't know, let's see. Now, do you remember the power developed? When we discussed the power developed, B developed is almost equal 1 minus S, or the power in the gap. Oh, the power developed, yes. So the power developed is almost 1 over S, the power in the gap, correct? Yeah? Yes? So simply, this one has a relation with what? With the efficiency, because the efficiency is equal to what? The power developed over Pn, yeah? So almost this means that the efficiency is equal 1 minus S.
Yes.
Yeah? So simply the machine which has a lower slip has a higher efficiency. Right? So simply this means that the class A has a higher efficiency than class D. Good? Now which one you will use according to your application? Yeah? If I need high starting torque machine without control, plug and play, I will go to where? Class D. If I'm having control, I will go to class A. Then I can shift the maximum torque any point I need. without adding a resistance. Later on we'll know how to do that by changing the frequency and the voltage, for example. Correct?
بس دكتور الشيء اللي هون ما فهمت كيف الافشنسي صارت واحد ناقص بس قسمنا maybe على
Now simply this is, let's assume that I am saying ideal case, which means that the power on the gap almost equal the power input, yes? What is the difference between the power on the gap and the power input? The copper losses on the stator, yeah? And the copper losses in the stator actually is negligible compared to the actual power, correct? Yes? So roughly speaking, let's assume that I'm living in the ideal case. So I will say that the power on the gap is equal, almost equal the power in. The efficiency is equal to what? It will be the power on the gap, or the developed power, over Bn, correct? Now this one, I'm living in the ideal case, Bn over Bn, and I'm having scaling, 1 minus S. So ideally, it will be 1 minus S, yeah? But S will never equal to what? To 0, yeah? Yeah? We know that if I need to plot the efficiency curve as a function of S, to be something like this, huh? Here S equal to 1, here S equal to 0. Huh?
Why?
Because if S equal to 0, the rotor is rotating by what? By the single speed. There is no induction. By the name, this machine is called what? Induction machine. If there is no induced voltage in the rotor, there is no developed torque. Yeah? Yeah. So if there is no developed torque, there is no power. So the efficiency equal to what? 0.
دكتور اذا حطينا مثلا بدل بي ديفلوب بي اوتبوت مش الكلاس A الروتيشنال لوسز اعلى ولا لا؟
Now let's see. The rotational losses due to what? Due to what the rotational losses? Due to the bearing. The bearing. Yeah, the bearing, which means that in general we are designing the machine such that it has what? A good bearing system, such that the rotational losses is negligible. But there's a rotational losses. Why? Because I'm having moving part. Yes? Moving part. They are interact to each other. Of course there will be friction. But this friction is what? Is very small. Yeah? Someone will say, I'm having what? You are neglecting the copper losses on the rotor, for example, here. But this is what ideal case. Huh? In order to judge about the efficiency from the slip. Yeah? Someone will say, you are neglecting also the core losses. Yeah? The stray losses. You know that I'm having core. Yeah? I'm having core. So there will be what? Hysteresis losses, eddy current losses. Correct? All of that, sometimes we say it's lumped together and dumped where? In the copper losses of the state. Yeah? But another time, this is negligible compared to what? To the actual power. Yeah? So the main, let's say, losses are the copper losses on the stator and the copper losses on the rotor. If I'm giving you rotation losses, you will take it. If there's no rotation losses and there's no hint to calculate, you will assume the rotation losses is equal to what? To 0. If there's no hint about the core losses, it will be what? 0. Otherwise, I will tell you that the copper losses is lumped to what? To the stator losses to be blah blah blah. Yeah? Do you have any questions here? So in summary, if I need to calculate the torque, I will use the following relation. Now, the first thing, this is what? Mechanical speed or electrical speed? Do you remember the power developed over what? Omega S mechanical. So this is the mechanical speed. If I need to use the on-shelf speed, which is the 2 by F. Now 2 by F is correct equal to the mechanical speed if the number of the balls is equal to what? 2. Yeah? If not, and I need to use the electrical speed, in this case, this is omega S mechanical. Huh? So in this case, what I need, it will be what? Do you remember the relation between the mechanical and the electrical? Yeah? Omega mechanical will equal 2 over P, omega electrical, so this will be P over 2. Yeah? Multiplied by this TD. Correct? In this case, this omega will be what? electrical. And omega electrical, we know that it will be 2 pi F1. Yeah? Now, most of the time you don't see this one. Why? Because I'm having 2 poles. Yeah? But simply, in order to be in the safe zone, use the mechanical synchronous speed. Yeah. Use the mechanical synchronous speed. It will be 2 over P multiplied by omega S. Yes? Yeah? Or, if you don't know this one, calculate an S. Yeah? Calculate an R. If you have an R, then convert it to what? To omega R, and this will be the mechanical. Huh? Now, we have the large slip, which is the starting region, let's say, or the nonlinear region, or the unstable region, which means that the torque can be approximated in the following relation. Here, I can have information that the torque is inversely proportional with 1 over S, correct? And we have what? The small slip region, or the steady state region, or the linear region. And here, what I'm having information that the torque is proportional with this, correct? Yeah. And I need the maximum torque and the maximum slip. Now, either you will memorize this one, and this one. Those, even if you don't memorize, you can get it directly. But simply in the exam, if you need to differentiate and equal to 0, you will, let's say, spend 5 minutes, 10 minutes. You don't need to do that. Yeah? Simply, those are the 3 relations that you must memorize. The second thing, you should understand how I did calculate the developed torque. Because imagine I'm changing the configuration and I'm connecting external resistance to the rotor. Or I'm connecting external supply to the rotor. Like double feed induction generator. The double feed induction generator actually is what? Induction machine where the rotor also I can what? Inject a voltage. Yeah? Yeah, but simply if I need to inject any voltage on the rotor circuit, I must respect the frequency of the rotor. Yeah? Otherwise, I will do a short circuit, circuiting current. Yeah? So in this case, if this is the case, you need to know how I can define or calculate the developed torque. Yes? It will be the same. Calculate the I, square it. Yeah? Then if I multiply it by what? By 1 minus S over S R dash, I will get the developed torque over the speed. I will get what? The developed bar over the speed. I will get what? The developed torque. Yeah? So this is very important. How we calculate the torque. So if I need to find the starting torque of the induction machine, then S equal to what?
1.
S equal to 1. Now, if I need to control, or what will happen if I change the voltage? Changing the voltage will change the no-load speed. This one?
No.
No. Changing the voltage will change what? The maximum has what? A relation with what? Now, if I recall, TE or TD is proportional with V squared, correct? T max is also proportional with V squared. Yeah? So, simply, this means that if I'm changing the voltage, and if I need to change the voltage, I should not exceed the rated. So let's assume here I'm having 2 curves, V1, and V2 is less than V1. So the first thing here, those will be shrinked, yes? Now the current will change, yes, will change. Why? Because the current is equal to V over Z. If I'm not changing the frequency, Z are the same. So I'm reducing the voltage, so I'm reducing the current. If I'm reducing the current, I'm reducing what? The starting torque. Yep. So this means that if I'm changing or reducing the voltage, I'm shrinking the curve, correct? It's like I'm shrinking the curve. But S max has no relation with the voltage. So all the time, the maximum torque will appear at the same time, at the same location here. Yeah. But simply what we'll do, I'm shrinking, let's say, the voltage. Yeah.
ليش الفرق بالماكسيموم كثير أكبر من الفرق بالستارتنج؟ الفرق بين الماكسيموم أكبر بكثير من الفرق بين الستارتنج.
Now, even if I put the torque speed characteristic of the machine, now this is starting and this is the maximum. There's no relation between this one and this one.
بس أنا قصدي تنتين في تربيع عشان هيك مثلا.
Yeah, but simply if v square, the factors are not the same. If the factor is not the same, then the relation is not the same. The factor in between is not the same. Yes, the TE, for example, the starting torque is also proportional with what? T start is proportional with V square, correct? But the proportional gain here is different than here and different than here. This one and this one is not the same. Yeah, correct? So if the factor is not the same, this means that the scaling will be not the same. Yeah? So someone will say this is a method to control the speed, correct? Changing what? The stator voltage. If I'm changing the stator voltage, what will happen? I'm shrinking the torque speed characteristic. Let's assume that I'm having the following torque speed characteristic. Let's assume C. Then I'm having what? I'm going from speed 1 to speed 2, correct? Yeah? Yeah, yeah, so simply here I'm having narrow range of controlling the speed, correct? Yes? You see? It's narrow. The second thing, what about if I'm having the following torque speed characteristic? What will happen? Yeah, correct? So simply here, if I'm reducing the voltage, I'm reducing the maximum capability of the machine. So simply someone will say, this voltage control is restricted. Sometimes we say that you only allow to change the voltage between 0.5 the rated until the rated. And in this case, you will have what? A narrow speed region to control the machine. So nowadays, it should be used. No one uses this method nowadays. Why? Because simply it what? The first thing, I need a mechanism in order to change the voltage. I have a mechanism, yes I have. Someone say I can use auto transformer. Someone say wait. Auto transformer, this means that you need a human to change the turn ratio in order to adjust the voltage. Okay, someone said that I will use what? Voltage control, power rectangles. Yes? You say okay. But simply if you use power rectangles for only gaining a small advantage, controlling the machine in very, very narrow region, it's not worth it. Yes? Okay. So in general, this one is what? Is restricted between 0.5, so the voltage here, greater or equal 0.5 V rated, less than or equal V rated, you are not allowed to impose a voltage more than the rated. Yep. And this one has what? A narrow speed region to control the speed in. Good. But simply someone will say, what about if I'm having class D? Class D machine. In this case, yes, this machine can be used. Yeah? Class D has a wide speed region, so I can control the speed in all the region using what? Using the stator voltage control. Yep. Okay. And here the speed is controlled below the rated speed. Yep. 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 So I cannot control the speed above the rated using voltage control. It's impossible. Yep. Because I can't impose what? A voltage higher than the rated. Now, if I need to adjust the rotor resistance, and this is only applicable for what? For the one rotor. Yeah? Now let's see. Changing R2 will reduce what? I2. but it will what? Increase the S max. So I'm shifting the S max toward the starting, right? Yeah? And the T max has no relation with what? With R2. So this is advantage that I can shift the maximum torque until where? Until the starting by adding external resistance. Yep. So simply here I'm having what? 3, let's say, scenario where I'm adding a resistance. Yep. So which one is written here actually? Now R add 1, this one actually, let's assume this one is R2 dash, which means that R external here equal to what?
0.
Equal to 0. Then if I'm adding a resistance, what will happen? Now T max is not changing, but what I'm changing? What I'm changing? The maximum. So I can shift the maximum torque such that I can put it where? As S max 3 equal to what? To 1. Yeah? But this is only valid for what? For one rotor machine. Yep. Now the same thing if I'm assuming the following torque speed characteristic. In this case, I can control the speed. This is N1, this should be N2, and this should be N3. Good. Again, T max has no relation with what? With R2. Yeah? Now, okay, let's assume the following example. If I'm having wood rotor 3-phase induction machine which has a stator resistance 3 ohm and rotor resistance referred to the stator 2 ohm, the equivalent inductance is 10 ohm, I need to calculate the change in the starting torque if the voltage is reduced by 10%. The meaning is what? I need to find a ratio between the starting point referred to the rated. If I'm reducing the voltage to be what? 0.9 V rated, the meaning, huh? Then I need to calculate how much rotor resistance I need to add to the rotor in order to achieve maximum starting torque, which means that T max should be equal to what? Or S max should be equal to what? 1. So the straightforward one is what? To calculate S max, put S max equal to 1. In this case, I'm maximizing what? The starting torque. So the first one, how I can calculate. Now, if you don't remember any formula, but only you remember what? That T start is proportional with V square, correct? Yeah? Yes? So you will say that T start rated is proportional with V as rated square, correct? So T start at 1 is proportional with V as 1 square, correct? So if I'm taking the ratio, let's say T1 over T rated will equal to what? V 1 square over V rated square. Yeah? Correct? So this equal to what? 0.9? Yeah? Square. So this will equal to what?
0.81.
0.81. Yeah? So how much reduction I will have?
90%.
Yes, which is almost 20%. Yeah, almost 20%. So simply, if I'm asking question, 20% reduction in the voltage. How much reduction in the starting torque I will do?
0.36.
0.36. So I'm having 20%. 0.8 square.
164.
0.64. 1 minus it is the reduction. Correct? Here are the same 0.9 square, 0.81. 1 minus it is 0.19. Correct? Now, I need to calculate what the external resistance I need to add in order to achieve the maximum torque. So the most straightforward to solve it is to say that S max must equal to 1. Correct? So this is up. So S max, which equal R2 plus the added resistance, correct? Over the the R1 square plus X equivalent. This one's given, this one's given, this one's given. So I need to calculate this one. If I do the math, it will equal 8.44. If I need to calculate how much losses, yeah, is there due to this modification.
I square.
Yeah, I square multiplied by this one multiplied by 3. Yeah, 3-phase system. Yeah.
I2 I square في R اللي جديد.
The rotor resistance. The rotor current.
الروتر كمان بحسب من أول جديد صح؟
Yes, because you are changing the impedance, of course. Yeah. Do you remember the equivalent circuit now? Now, if we assume that this is the RS, XS, XR dash. Here I'm having the R dash over S. Now this one is modified. Huh? This one's changed. Yeah? If this one's changing, and here I'm assuming that this is the magnetizing branch. Now here R dash, or sometimes we call it I2, will change. Yeah, it will be V S over Z new, correct? Yeah. Then you need to calculate this one. Then square it, multiply by the external resistance you need to add, multiply by what? By 3.
دكتور عندنا امتحان بعدين.
Okay, I will stop here. I think